Welcome everyone. Today we are very pleased to host Dr. Eloisa Poggio, a researcher at INAF, Osservatorio Astronomico di Torino. Eloisa obtained her PhD in physics and astrophysics from the University of Turin in 2018, and since then she has held several prestigious research positions, including a Mary Fellowship in Nice. In recognition of her scientific achievements, she received the Lorenzoni Prize from the Italian Astronomical Society in 2019. Her research interests include the structure, kinematics, and chemodynamics of the galactic disk, with a special focus of non-axisymmetric features such as the galactic warp, spiral arms, and bar, as well as phenomena related to galactic seismology. Today, she will guide us through the latest insights into the tridimensional structure and chemodynamical evolution of our galaxy, highlighting recent discoveries enabled by Gaia and complementary stellar surveys, and offering a preview into the developments expected from future data releases. Please join me in welcoming Eloisa. Eloisa, thank you for being with us today. The floor is yours.
Good morning, everybody. Thank you very much, Julia and Fateme, for the kind invitation and introduction. So yes, this talk will be about the disk of the Milky Way. So we can start with an apparently simple question. How does the galactic disk look like? And as you will see in a moment, the answer to this question is not trivial. Everybody agrees that we live in a spiral galaxy, but there's no consensus on the geometry of the spiral structure of the disk of the Milky Way. And so there's a great variety of papers trying to face this problem by constructing models and maps of the spiral structure of the Milky Way. Here you see three important examples. One is based on H2 regions, model from Georgelin and Georgelin 1976. It is based on 4 spiral arms. This is the Sun and this is the galactic center. The model in the middle is based on neutral hydrogen emission, again based on 4 spiral arms but with a different geometry. And then on the right panel you can see the model from Reed based on masers, which includes more than 4 spiral arms. Specifically, it's interesting to see this segment called local arm, which is called local because it's close to the Sun, and it is a relatively minor segment in this map. So it is interesting to see that if one tries to overplot these 3 models, the geometry is quite different. So I think we can really say that there's no consensus on the spiral structure of the Milky Way. And recently with Gaia data, it became possible to map the distribution of young stars in the galactic disk, and specifically for a sample of 600,000 upper main sequence stars. So this means OB, mostly OB stars, also some A stars, and map the over and under dense regions in the galactic disk. So here in this map, the white cross shows the Sun's position, the galactic center is to the right, and galactic rotation is going clockwise. So as you can see from this map, the distribution of young stars is not homogeneous. There are some overdense regions and some coherent structures. We can identify 3, maybe 4 major features. One is the segment of the Perseus arm. This is the segment of the local arm. And this is the Sagittarius Carina arm, maybe Scutum, but this is unclear. So these 3 features are clumpy. Part of this clumpiness might be real, but part of it might be due to extinction. So if we don't see stars along a given line of sight, it is possible that this is a foreground caused by foreground extinction, and it is a so-called shadow cone. So what do we learn from this map? We can compare this map from upper main sequence stars to previous models, and we can find very good agreement with one arm from the Revin model, arm number 2, this dashed line that you can see here in the left panel. Whereas in the right panel, we can see a comparison between the overdensity map of the upper main sequence stars and the model from Reed. The black crosses show the position of individual masers. If we compare the position of the distribution of the masers in the first and second quadrant with the position of the overdensities, I would say that we can see a good agreement with the position. But if we compare the geometry of the model to the map, we can see that the orientation of the Perseus arm, which is this line that you can see here, is different in the sense that these masers have been grouped together with these other stars, or to these other masers, whereas based on the upper main sequence map, the orientation of the Perseus arm would be presumably a bit different with a different pitch angle. It is also interesting to map the spiral structure with Cepheids. Cepheids are well-known distance indicators and very good tracers of young populations in the galactic disk. And recently, Dremel et al. Presented a model based on Cepheids, as you can see, we reach much larger distances. And so they find a model with 4 different spiral arms. And if we compare this model to the model from Reed, as you can see here from the right panel, the geometry is quite different. So the distribution of stars in the galactic plane is not the only interesting quantity. We can also analyze the vertical distribution of the stars in the galactic disk. And if we do that, we first of all can see that the disk of the Milky Way is not flat, it is warped in the outer regions. So it is bent, the disk is bent upwards in one direction and downwards in the other. And well, this feature is known as galactic warp. It has been known for a long time, actually. But recently it was mapped with great detail with the classical Cepheids, as you can see from these plots. And specifically here, you can see azimuthal slices of the galactic disk, and the Z distributions, the vertical distribution of stars, is a function of galactocentric radius. So you see that in some regions, the disk is bent downwards here, like this, and upwards in the other regions. The warp has been also mapped with older stellar populations like 2M star counts and reclam stars. Whereas, well, for the Cepheids, there's good agreement between different values in literature, whereas for older stellar populations, as you can see also from this plot and other works in literature, there's no consensus on the amplitude. Some people say that older stellar populations have larger amplitude compared to the Cepheids one, whereas other people say that the amplitude of the older stellar population is smaller. So it is much more uncertain, I would say, whereas the structure of the warp in the Cepheids seems to be relatively well constrained, because there is at least there is a very good agreement between the values in literature. So how does the galactic disk evolve? That's the next question. And of course, to answer this question, one needs the kinematics. And thanks to Gaia data, we found that the disk of the Milky Way is a very interesting place. There is a great variety of features and substructures in kinematics, including the phase spiral discovered by Antoja et al. 2018, but also moving groups, ridges in V5 versus R, where V5 is the azimuthal velocity of the stars and R is galactocentric radius. Also vertical symmetries and waves. So the disk of the Milky Way is a very active place where several phenomena might be at work, and this the disk has been presumably perturbed in the past, and we are detecting the scars of these perturbations today in the distribution of in the kinematic distribution of stars in the galactic disk. So we mentioned the warp a couple of minutes ago. If we look at the vertical motions, we expect the warp to manifest itself somehow. And if we try to model the motions of the stars, the vertical motions of the stars, we find that taking into account the uncertainties on the amplitude of the warp, we are not able to match the vertical motions of the stars unless we assume that the warp is not a static feature, where static means frozen in time and stars are rotating around the galactic center, but the warp shape is fixed. Whereas if we introduce a new parameter, at least one parameter called precession, we are able to match the vertical motions better. And recently, using CFITs, Dan and al. Found not only that the warp is precessing, but also that this precession rate varies with radius. So it's not just precession, but differential precession. So it changes with radius. And so this mapping was possible because CFITs reach very large distances. So it's not just a local sample, it's a sample that goes out to very large distances, though with, of course, smaller statistics, but still it is interesting to see that we are able to map the disk, a good portion of the disk of the Milky Way. And right, so we have discussed the three-dimensional distribution of the warp. We have discussed the kinematics. It is now interesting to ask ourselves how good these models are. And one way to do that is, just to look at the residuals. So just take the data, remove the best fit model, and see how the residuals look like. And so here I can show you some maps based on two different data sets. One includes young giant stars, and the second one is based on CFITs. So if we remove from the data the best fit model, assuming a S-shaped warp, so a classical warp, just a tilted ring where the disk is bent upwards in one direction and downwards in the other direction, so that's just a basic warp model. We remove the best fit model, and what we obtain is a map which is not dominated by Poissonian noise. It's not just Poissonian noise. We just see, we see some features here in red where stars are systematically shifted upwards here. So this dashed line is just to guide our eye. And blue, stars are systematically shifted downwards. So this is an almost radial feature, not exactly radial. But if we do the same, if we play the same game with vertical velocities, we remove the model of the warp, and the residuals again show a feature similar to the one that we saw in Z, but slightly shifted outwards. And so we ask ourselves, what's the meaning of these maps? And the shift between these two features, the fact that we see similar features in the residuals, but one is shifted with respect to the other one. And so we compared these maps to a simple model. So we assume the collisionless Boltzmann equation, an exponential disk, and just a corrugation. And then we impose that this corrugation is propagating outwards. And so the prediction from this very simple model is that the velocities, the vertical velocities are shifted outwards with respect to the pattern in Z. And so this shift that we see in the data can be interpreted as a signature of a wave, because it is an oscillatory behavior, a wave that is propagating upward. If we instead assume that a corrugation is propagating inwards and not outwards, so the pattern that we see in Z and VZ would be reversed. So we would have this feature, this red peak would be inwards, right? It will be shifted towards the inner parts of the disk. And this is clearly not what we see in the data. So the emerging picture is that there is a feature on top of the warp, which is consistent with the corrugation propagating outwards. And also it is interesting to see that the stars in the corrugation have also systematic radial motions. And so this means the stars in this region, so this region we can think of a simple ripple, right? Because it is almost like a radial feature. So we can think of a warped and corrugated galaxy. And the stars in the positive crest of the corrugation that we are mapping here have also some vertical and radial motions associated to it. If we compare this feature to spiral models available in literature, we don't find particularly nice agreement. But it's interesting to make this comparison because in principle, spiral arms can influence, of course, the dynamics of the stars and the motions of stars in the galactic plane. But of course, the picture is quite complicated. For instance, if there is a satellite galaxy interacting with a galactic disk, we expect to see some features, some substructures, as you can see in this nice animation. So the picture is quite complicated because there are internal mechanisms like the bar and the spiral arms, but also external perturbations like satellite galaxies, like the Magellanic Clouds or the Sagittarius dwarf galaxy. So the disk is a very interesting place because we have a great variety of phenomena and we can study them by mapping the distribution of stars not only in three-dimensional space but also in kinematics and metallicity, as you will see in a moment, to learn the dynamics of these phenomena and to learn more about our galaxy. So even if a star is born on a perfectly circular orbit, today, so at the present day, its orbital radius might be different because of different possible causes. One possibility is that blurring is taking place. So there is a perturbation that increases the epicycles, and this perturbation can happen both in the in-plane and in the vertical direction, according to Selwood and Binet. And this is also called orbital heating. And the second reason is churning. So there is a non-axisymmetric pattern, like spiral structure, for instance, which exerts a torque on the star, and it can lead to a change in the angular momentum of stars and therefore mean orbital radius. So if we combine these two effects, then we can see this plot from Frankel et al. 2018, where we see the probability distribution of orbital radius as a function of time. And so this probability distribution broadens as a function of time, and the strength of radial migration determines the rate at which the distributions broadens with time. Of course, in this context, chemical cartography is very important. So it's very important to map the amount of metals in the galactic disk. And so the mapping of the radial metallicity gradient of the Milky Way has been done with different tracers, including Cepheids, open clusters, and giant stars. So this is a very important aspect, of course. And so as you can see from this model from Minchev et al. 2013, the disk of the Milky Way is seen to grow from the inside out with time, and radial migration is a strong function of radius and time. And recently, Radcliffe et al. Mapped, well, first of all, they estimated the birth radii of stars from a sample of apogee stars, and they recovered the cosmic evolution of 6 apogee elements. Right. If we map the mean metallicity of stars in the galactic disk, then what we see is different depending on the type of population that we are adopting. For instance, if we select young stars, we can see, so this map is based on young stars, young giants. The sun is here, galactic center is to the right, and as you can see from this map, there is a net decrease of metallicity towards the outer parts of the disk, and this is expected because of the radial metallicity gradient. But it's not just a smooth gradient, there is also some substructure. So if we cut the disk in different slices, as you can see here from this dashed lines. And we see the variation of mean metallicity as a function of radius. We can see that there is not just a smooth decrease, there are several bumps. And these bumps, so the black points, let's just focus on the black points. The black points somehow correlate with a spiral structure. There's not a perfect one-to-one correlation, and this might also tell us something, as we will see in a moment, but they tend to be correlated with the position of the spiral arms in the galaxy. So as you can see, it doesn't even make sense to talk about one simple linear gradient, right? Because these fluctuations are so pronounced that it is more appropriate to talk about chemical azimuthal variations. So we see these undulations that change depending on the position in the galactic disk. On the other hand, the older stars have a very smooth behavior, as you can see from the open circles that you see here. So the black dots are young giants, the open symbols are for the old giants. And you see there's a very smooth decrease, but the slope changes as a function of azimuth. So there is an azimuthal dependency also for the older stellar populations, where the slope of the gradient changes as a function of galactic azimuth. And so if we compare the metallicity axis to the geometry of the spiral arms that we discussed before, we can see that stars tend to be more metal rich in the arm regions, whereas they tend to be more metal poor in the interarm regions. Do we expect to see something like this in the disk of the Milky Way? Yes, we do. For instance, here, this is a very, I think, very nice paper from Kopriskov and collaborators 2018, where they analyze a simulation where they impose a spiral arm potential, and they have two different populations. One is dynamically cold, so with small velocity dispersions, and it is metal rich, whereas the other population is dynamically hot and metal poor, and they let the system evolve. So here you can see in the first column, you can see the density at the 3 different times. So you can see the spiral structure here in the density. In the second, the third, and the fourth column, you can see the metallicity axis, assuming 3 different initial gradients. So as you can see here, we do expect stars that are located in the arm regions to be more metal rich, typically more metal rich than the interarm regions. But there's no one-to-one match necessarily, and it really depends on the initial gradient. Also in this other plot, you can see that the dynamics of the spiral arms can have an imprint also on the metallicity. For instance, here you can see that stars close to co-rotation from this model from Spitoni have a larger signal in the metallicity, but also there's the bar. The bar can induce azimuthal metallicity variations, and also radial migration induced by the Sagittarius dwarf galaxy. This is the radial velocity, so radial migration, and which in turns, as a consequence, manifests itself as chemical azimuthal variations as well. So the picture is quite complicated. This is my conclusion. We see a great variety of features in the galactic disk, the spiral structure, the warp. We are now making progress towards the mapping of these features. We can also map the kinematics and chemistry, and this is very important. We can learn a lot. And since this is a WST seminar talk, I think it's important to say that WST can make an important contribution to our understanding of the mechanisms governing the evolution of the galactic disk. This is the end of my talk. Thanks a lot for your attention.
Thank you, Eloisa, for this very interesting picture on our galactic disk. it's time for questions and discussion. I have a question on the slide on chemical azimuthal. If you go back to this slide.
This one?
Okay, exactly. Can you tell again better the origin of these bumps?
Yes. Okay, so the origin is unknown, of course, but one proposed explanation is that the stars in the galactic, in the that are in the spiral arms tend to be more metal rich than those in the interarm regions. So, in other words, this is, if we just take a slice of this map, you can see that there is a red and then blue, and then green and then blue again, and then greenish again, right? So this means that we are jumping from metal rich stars and then metal poor, and then metal rich again, and then metal poor again. Of course, there's also a trend as a function of galactocentric radius because of the metallicity gradient. But the fact that there are these fluctuations, and the fact that these fluctuations are not occurring, randomly in the galactic disk, but they are somehow tracing the spiral structure, suggests that the spiral arms might be at the origin of these features. So these bumps might be a signature of the spiral arms. This is for the young stars. For the old stars, we also have to remember, well, in general, of course, we have to remember that there are also a great variety of other phenomena taking place, like the bar and random migration from satellite galaxy, etc. But at least for the young stars, since there is this correlation between the position of the spiral arms and these bumps in metallicity, one possible explanation, I would say a reasonable explanation, is that they are correlated because the mechanism might be related to the spiral structure.
Okay, thank you, Elisa. There are other questions? Seconds. No questions. Okay, I think that we can stop the session here. Thank you, Eloisa, for this interesting talk and sharing your work with us. And to all of you for participating in the talk. Next talk will be led by Professor Anupam Bardaj on July 15. Thank you and have a great day. Bye.
Bye.